everyone, today we are going to be going over a calculus tutorial video series, and today we're focusing on functions, their domains, ranges, and graphs. Now, since functions are a fundamental basis within calculus, overall there is some backbone that is already covered inside of algebra, but to be able to cover the basics as we are ranging over the different forms of complexities for this whole video lecture series, we're starting off with the basics to be able to get them out of the way and to be able to cover the fundamental understanding prior to going over to more complex concepts in calculus such as derivatives, integrals, and eventually multivariable calculus. So, just to be able to get things started, we're going to start breaking down by understanding the principle of what a function is, and then move over to the different types of functions there are with the respective domains, ranges, and graphs, along with a couple practice problems as well to be able to help solidify our understanding. And so, to be able to get started, so a function in general is regarded in this following notation. The symbol f represents the function. F represents function. And the letter x is regarded as the independent variable. And y is considered the dependent variable. For within f, referring to our following function, it is also denoted as y is equal to f of x. And within calculus, there are a wide variety of functions that express different outputs with their respective domains and ranges, which we are going to head into right now. And now we're just going over one of the most basic functions in algebra and in calculus in general. We're going to be linear functions. So, linear functions are typically denoted by the equation y is equal to mx plus b. Let me just write this down. We're breaking down the whole equation. Y is considered the dependent variable. M is going to be considered the slope, which is also equal to the rise over run. And x is going to be the independent variable. And b is going to be considered the y-intercept. So, breaking down with what we have over here. So, if we were to pinpoint a given example, let's just say, for instance, we have an equation over here of y is going to be equal to 2x minus 1. Just note that here. So, we already know in particular, whenever we break down the following equation, let me just go up. So we notice that we have y, or dependent variable. We have our slope, where it's m, as noted, and m is going to be considered 2. And then we have x as the independent variable. It's just meshed in with 2 over here, and it's just held as a constant. And then meanwhile, the y-intercept, we note, is -1. So b is going to be equal to -1. And then when we break down the following graph that we have over here, let me just zoom in further. We notice that over here, we see these dots. So we have a dot at -1. Let me just erase this part here. And we also have a dot over here. Now, the reason why we have these dots is because, one, this dot here is considered the y-intercept at -1. Then we go up 1, 2. So we have 2 of them over here, and then we go over 1, representing 1 here. And so we're able to determine exactly the nature within our linear function in general, where we have our slope, where 2 is going up, and then we're moving over to 1 on the right, and we see our y-intercept being -1 right here. And overall, between the domain and ranges, the range represents really the y, and the domain represents the x-axis. We notice right here between the domain, it can go as far to the left as possible and to the right, hence infinity as usual. And then range also operates in the same way. And we also need to denote that our slope, m, which is denoted as rise over run, is denoted as y2 minus y1 over x2 minus x1, just as a general formula. Let me just write this out clearer. So we have our slope m is denoted as rise over run, and this is the formula that we rely on for linear equations for our slope. And now let's head over to our first practice problem. And now let's go over our first practice problem. So we need to develop an equation that's going to be going through the points 2 to 3 and 4 to 7. Now, whenever we see this notation, this means that x and y, these are the following points that we see on an x and y axis. 2 and 3 would be, so since we would count 1, 2, and then on the y-axis 1, 2, 3, that point would be located right here, and then 4 and 7, we would go 1, 2, 3, 4, and then we would go all the way up on the y-axis 1, 2, 3, 4, 5, 6, 7. Let's draw this up and then just move this y-axis over here. So we have 7 here and 4 there. That means that that's going to be located at the intersection between these 2 points. Now what we need to do is that we need to develop a linear equation, where a linear equation, as we all know, is y is equal to mx plus b, where y is going to be the dependent variable, x is the independent variable, m is the slope. In fact, I'll just write this out here. So y is equal to the dependent variable, x is equal to the independent variable, m is the slope, which is equal to rise over run, and then b is going to be the y-intercept. I'm going to introduce a concept for the slope equation. For actually the slope equation, when we mean rise or run, it's typically denoted as y over x, but the slope equation is going to be y2 minus y1 over x2 minus x1. Well, what does that mean? Well, it means namely that whenever we are seeing these 2 different points that we have to denote exactly which one is going to be further out. So what we mean by that is, so we would have 4 and 7 and 2 and 3 as our points. We already know that 7 is y, 4 is x, 2 is x, 3 is y, and we can also write the equation as we know as 7 minus, looks like 3, over 4 minus 2. Well, we know now that the slope, when we subtract both of them together, are going to be 4 over 2, which it looks like 4 divided by 2 is going to be equal to 2. So our slope is going to be 2. So when we are writing out our equation, we have y is equal to 2x plus b. However, we got to figure out exactly what b is. Well, what can we do? Well, an idea that we can actually do is that we can actually substitute an x and a y. Since we already have an x and a y here, we can do, I'll just do this in another, 3 is equal to 2 over 2 plus b. It looks like 3 is equal to 4 plus b times 4 minus 4. It looks like negative 1 is equal to b, or b is equal to -1. So once we've already found that, we are actually going to put that in our full equation. Therefore, our whole formula altogether, we've already figured out what the slope was as 2. We already plugged this in, and to be able to figure out what the y-intercept is, we plugged in x and y into this, and then our equation is going to be equal to y is equal to 2x minus 1, since we have the -1 here. And that is our answer. Feel free to take a screenshot of this part as well. And let's over to our second practice problem. And so let's consider our second practice problem. Here we have our given equation, y is equal to 3x plus 7. And what we need to do is that we need to plot exactly our linear function. And we know that our linear function, if we wanted to know from numbers all the way to the main equation, we know that it's y is equal to mx plus b, where y is going to be the dependent variable. X is going to be the independent variable. And then m is going to be considered our slope, which is rise over run. And then b is going to be the y-intercept. And so whenever we have our following equation, and we know that y is equal to mx plus b, we can just match up the numbers accordingly. So we know that our y-intercept is going to be 7, so b is going to be equal to 7. And then our slope is going to be, it looks like 3. And our slope is always rise over run. And typically whenever we see a number right here, there's this tiny little fraction down here that is a 1. So we have 3 over 1 is technically our slope, which is typically denoted as 3. And just based on this information alone, we can actually start plotting our linear graph. So we know that we have our x and y axis right here. And if we want to, we can start with the y-intercept. So we can go 1, 2, 3, 4, 5, 6, 7. And we know in a y-intercept, what that means is that it's going to hit at the y-axis over here. So we have a 7. And what does it mean by rise over run? Well, whenever we have our slope right over here, that means I'm going to need to move this up a bit. So just give me 1 second. I'm going to move this down just a bit, and I'm going to move this down just a bit. I'm just going to move this as well, because I kind of have to, for the sake of moving. Okay. All right, there we go. So that means so we can count all the way from 7 at this point to 1, 2, 3, and then we move over 1. So that means on our x-axis, let me just point this out, and it's completely arbitrary. So whenever we have our slope, we do 1, 2, 3, and then 1. So this is where our line is. So we can just plot it this way, and this pattern will continue. So we can go up from this point another 3 dots, then over 1 as well. So we can go 1, 2, 3, and over 1. This is where the next dot is. And this is how we plot our linear function. Feel free to take a screenshot of this as well. And now let's head over to quadratic functions. But let me just zoom out and clean it up for you folks. Now feel free to take a screenshot of this, and let's head over to quadratic functions. And now let's go over quadratic functions. So quadratic functions are typically denoted as y is equal to x squared, where we have our following function over here, with respect to the domain and range, our domain being the x-axis, our range being the y-axis, domain is going out all the way out far to the left as denoted by negative infinity, and all far out to the right as denoted by positive infinity. The range, on the other hand, focuses on all real numbers, including 0, to positive infinity, hence going all the way up. And there are two parts that really become part that construct quadratic functions. The vertex, which is denoted as this dot over here, the pinnacle, and then we have the axis of symmetry, which is an invisible line which goes all the way down, far to the left and far to the right. And typically, it's like a mirror between one side to another. And with quadratic functions, there are three typical equations that we will have to keep in mind. Our basic algebraic function of y is equal to ax squared plus b of x plus c. Then we would also have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then finally, we have our vertex equation, which is denoted as y is equal to a of x minus h squared plus k, where h and k represent the vertex. And now let me just move out so we can get a good, clear idea. Let me just move this over. Feel free to take a screenshot of this part, and now we're going to head over to our first two practice problems. Now in our first practice problem, let's go over the following equation. So we have y is equal to x squared minus 1. So typically when we have a following graph that we have over here, we have a y and x, 2, 3, 4, 5, 2, 3, 5. And whenever we denote our following equation, we always need to check exactly what slope is, where slope is typically denoted as m, which is rise over run. And it's also y2 minus y1 over x2 minus x1. And then b is typically our y-intercept. We can take parts from our linear equation and apply it here, but in this case we have x squared minus 1. So if we were to actually graph, in particular, what our equation will be, it looks like our slope is going to be 1 over 1 to be able to start with. 1, 1, 1, 1. Since we're dealing with a quadratic equation, we're going to have two different points in general. However, our y-intercept is going to be negative 1, so that means it's going to have to be pinpointed right here in this area. And it looks like 1, 1, 1, 1. This is just the basics of how we graph our quadratic equation as a first warm-up practice problem. Now let's go over another one that's a little more complex. Now let's go over a second practice problem. So we are given our quadratic equation, y is equal to 2x squared minus 4x minus 1. And in quadratic equations, there are three equations we rely on. We have y is equal to a of x squared plus b of x plus c. Then we have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then for the last one, we have a vertex one where it is known as y is equal to a of x minus h squared plus k, where h and k are denoted as the vertex. And h is referred to as the x of the vertex, and k is referred to as the y-intercept of the vertex. So for us to be able to figure out exactly what we need to do, the number of steps that we need to follow are going to be: 1, we need to figure out the vertex. Second, determine axis of symmetry. Third, calculate the y-intercept. And then finally, sketch the graph. Do so with the following. In order for us to figure out what the vertex is, we're actually going to be relying on this bonus equation, strangely enough. So it's denoted as h b over negative 2a. And for us to be able to figure out exactly what we have, so we have our following equation. We can actually figure out what a, b, and c are. So we already know that a is going to be referred to as 2. So we can just write it down 2 over here, and then b will be denoted as negative 4 right here because of this negative, because the minus sign that's right here, that'll be denoted as a negative. And so we have negative 4 over negative 4, which is then put back to 1. And now what we can do, since we already figured out what h is, and we need to figure out what k is, what we can do is that we can actually just plug in k, because this trick focuses on figuring out what the y-intercept is. So we can figure out, if we were to plug in k for y, we can then determine squared minus 4x minus 1. Since we can plug in both of these points together, not only are we going to plug in k, but we're also going to plug in h. So we'll have k is equal to 2, looks like 1 here, squared, minus 4, 1, minus 1. K is equal to, looks like 2 minus 4 minus 1, and all together we have negative 3. So we determine that h and k are denoted as 1, negative 3. That's where our vertex is located. So we determined that our vertex is 1 and negative 3. The next part is determine the axis of symmetry. And the axis of symmetry is the vertical line that passes through the vertex from what we already given our concept example and concept overview. There's an invisible line that showcases as a mirror. And in order for us to be able to determine our axis of symmetry, we can set up the fact from what we already got from h of k. It looks like that our axis of symmetry can actually be converted from what we got from h already, and can be set up as 1 and then we calculate the y-intercept. We do so whenever, so by definition what the y-intercept is whenever whenever a line passes through the part on the y-axis when it hits 0 over here. So what I mean by 0 is actually when the x-axis turns 0, the y-intercept is the point where the line will actually hit whenever the x is 0. And to do so, we can actually just plug in for our equation. So we have our equation, y is equal to 2x minus 4x minus 1. We could just plug in 0 to be able to get our output. So that would also mean 2 squared minus 4, 0, 1. After we do the math and everything, and we multiply everything all together, we know that the y-intercept, it looks like it's going to be negative 1. And we plugged in x for 0. So therefore, our y-intercept is going to be 0 and negative 1. Finally, we sketch a graph. So for us to be able to figure out our entire graph, we can actually set up a replace. So I'm going to put down the lines 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's y, not 5. Since we already have a vertex being 1 and negative 3, where that's the x and y, be 1, 2, 3. So we have negative 3. Let me just put this right here. And for us to determine the slope, remember when we went back on our linear equation and we actually determined what our slope was? Our slope is always denoted as rise over run. And whenever we see our slope, there's always a small little fraction that's underneath if it's just a whole number. Maybe a 1 right over here, so it will be 2 over 1. And so that means it will go 1, 2, and that means it will be going to the left, right over here. It'll still go up, 1, 2, and goes to the left. So left over here, and so on and so forth. And so since it is also squared as well, it will go up 1, 2, to the right. And look, we see our y-intercept over here. So we have 0 and negative 1. So it's going up. I'll use another color. 2, 1, 1, 2, 1. There we go. We see the dots. It goes up, goes up, goes up. Probably draw this better. Goes up. 1, 2. There we go. We'll just keep going up. Let me just move this out. And all right. Feel free to take a screenshot of this part as well. And let me just wrap this up all together so we see the whole part. Now feel free to take a screenshot of this part as well, and let's move over to our next part for functions. And now we're going to deal with semicircle functions. So overall, semicircle functions are denoted by the following equation: y is equal to the square root of 1 minus x squared, also denoted over here, and the domain refers to real numbers between negative 1 and 1, inclusive to negative 1 and 1, hence the brackets over here. And then we have non-negative real numbers between 0 and 1 within the range, for we know that the domain refers to the x-axis and the y refers to the range over here. Just need to zoom in for a second. And so, always to keep in mind whenever we're dealing with circles in general, the radius is always going to be 1/2 of the diameter, or you can just put in diameter divided by 2. And that would also give us our range. Just for context and just to be able to help cement the idea further. Let me just zoom out of here. And now, in this case, so if we were to have a positive semicircle, it would be denoted as this. But if we were to have a negative semicircle, it would typically be denoted by this: y is equal to negative square root 1 minus x squared. The negative is typically in the front, and we would have the same range as in distance-wise, but in this case it would just be at negative 1 in this case over here, and it would still have the same domain. So we have 1 and 1 over here. So that's for further context, and then this is also 1 up here. Okay. Now that we got all this stuff out of the way, let's head over to our first practice problem. And now let's go over our first practice problem. So in our first practice problem, we're given f of x is equal to negative square root 16 minus x squared. And so what we need to do in terms of graphing the whole function, we also need to do the following steps. 1. Determine the domain and range. And second, find the vertex. Luckily, there's a bit of a hack to this, which I'll showcase soon. So we always know that domain is going to be equal to x, and range is going to be referring to y. So whenever going our first step, what we need to do is that we can actually do this thing where we can just take out the negative and as well as the square root, and we can just denote 16. Actually, I'm just going to use this different color. We do 16 minus x squared is greater than or equal to 0. And so once we do some algebra over here, negative x squared greater than or equal to negative 16. And whenever we are divided by negative 1, to cancel out the negatives, this sign actually flips over. Just what they have. And then finally we square root. So x is going to be less than or equal to 4. And since we're dealing with the semicircle, altogether, since we have an x squared inside of a square root, we can actually already attest that we would have a negative 4 over here. So this would be our domain. Now to get the range, we have a different means to do so. Getting the range means we're focusing on the y-axis in general of how far up and down it will go. And we're also, whenever we figure out what a range is, that's actually where a vertex is going to be located. Because in the context of our semicircle that we have, since we do not have anything inside right next to the x squared, that means that the y-intercept will be at 0. And so when we have that predicament, x would mean at 0. And when we have that case, that means all we need to do, the range being f of x is going to be 0 less than or equal to y less than or equal to 4 in this case. Since we already determined that x is less than or equal to 4, we can also test that y in of itself would fall under the same circumstances as well. And to better clarify, what I mean in particular is that since we already have our domain already set up between negative 4 and 4, we can actually plug in values for x to be inside of our equation for f of x is equal to negative square root 16 minus x squared altogether, and then we determine our range. It's a bit of a tip and a bit of a hack that we have over here. And for us to be able to graph this, let's just move this over here. 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Since we have negative to start with, that means that we're going to have a circle that's going to be upside down, and we determine that our range is from 0 to 4, and then our domain is going to be from negative 4 to 4. So that means we have this point and that point, negative 4, 4, and then we have negative 4 all the way to 0. This is how our graph would actually look. And so yes, that is just the first problem that we have. Feel free to take a screenshot of this one, and we'll head over to our second practice problem. And now let's go over our second practice problem. So in our second practice problem, we have g of x is equal to the square root of 25 minus x squared. So remembering our steps that we have, 1, we got to determine the domain and range. Domain referring to x, range referring to y. And the second part, determine the vertex. And we always remember a little hack. If we can figure out the range, we can figure out the vertex. You got it. And so let's start off with the first part with figuring out the domain. Let me just zoom out of here so we actually understand. Different color over here. And so whenever we get rid of our square root, we have 25 minus x squared greater than or equal to 0. So we got 25 minus 25 minus x squared greater than or equal to negative 25. And whenever we divide by negative 1, this side always flips. So we have x squared greater than or less than 5. And since we are dealing with a semicircle here, this is actually, so a big point I need to highlight right here. So some people may think, oh, what if we were to add, for instance, having an addition right over here, just right here. Well, that's not going to be a semicircle at all. It's going to be a totally different graph. So actually it is denoted by having this minus x squared that really denotes that we're going to have a semicircle overall. Just a bit of a side note as well. But going back to determine our domain is going to be from negative 5 all the way to 5. So that means we can also have a test that will be negative 5 to 5. That's how we would denote it. And the range, on the other hand, this is where the magic happens. Since we already know, in particular, since we already figured this part out, and we're dealing with the semicircle, all we got to do between the range of g of x, it's just going to be 0 greater than or equal to y, and then, 0 is less than or equal to y, and then y is less than or equal to 5 overall. That is what our range will be. And since we are dealing with a positive side, this is where we also need to denote more. So we have x, and we have y over here. All inclusive. Whoop. That's not part of it. That's a totally different graph. Anyway, let's just go over here to determine our equation. Actually, I'll go right here. That's better. And so, drawing it out, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's going to be pretty easy. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's negative 5. 1, 2, 3, 4, 5. And that's positive 5. And since we are dealing with positive, our vertex is going to be at the top, since we have 5 all the way at the top over here. So let me just zoom out. And that was our second practice problem. Let's head over to our next function, which will be reciprocal functions. And now let's go over reciprocal functions. So reciprocal functions are typically denoted by f of x is equal to 1 over x. And the nature of reciprocal functions are really, really straightforward. If we were to go over the domain and the range accordingly, they're both going to be the same. Because since reciprocal functions are typically denoted as functions, there's always one general rule. We cannot divide by 0. And again, these functions are very, very straightforward. There's not that much to be able to go further in depth on. As long as we know the general rule, we can already pinpoint the nature of why they behave in such a manner. And without further ado, let's go over our first practice problem. So now, whenever we are focusing on our first practice problem, we are given the case of when we have 1 over 2 minus x, and we got to figure out how to graph it. Well, again, as we know with the general rule, cannot divide by 0. And reciprocal functions are typically always going to be the same, to an extent, depending on exactly what we're getting. So nature / structure would be the same. So all we got to ask ourselves is, what can we plug into x that will give us 0? Which will give us 0. We can even you can also plug in at the same time, but it's very straightforward that if we plug in positive 2 in this case, just positive 2, we're going to get 1 over 0, which is very self-explanatory. So therefore, what we can say with our graph, let me just move up. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3. Okay, there we go. So that a reciprocal function is going to be denoted right over here. So whenever we are hitting 2, in this case, and y is 0, so we have x and y, which is 2, 0, that is where it completely intersects. So we would have, in our case, negative infinity all the way to 2 in unison, 2 to positive infinity for our given domain. The range, on the other hand, would likely be the same, 2 unison, 2 infinity over here. However, a big however, we also need to figure out exactly what the y-intercept is going to be. And it's pretty self-explanatory. Whenever we have the y-intercept, that would be when x is 0. And so we would, I'm just going to move this up a little more. There we go. So that way we can denote that our intercept over here is going to be, looks like, when x is 0, then we have 1/2 over here. 0 at y. Intercept. And so, yeah, this is our first practice problem. Now let's head over to our second practice problem. Now, for our second practice problem, we're going to have our following function. Y is equal to 1 over x minus 3, where in this case, what we would have is, we can actually just pinpoint our graph over here. We just need to figure out exactly one where the reciprocal function will split. Then afterwards, where the y-intercept is located. Those are just the big 2 points that we have, so let me just put our y and x-axis. We're going to figure out what the domain ranges are. So we have a bit of a hack whenever we are doing this. So in this context with what we have, we can actually determine where specifically our axis of symmetry is going to be located. So since we have this -3 over here, it's actually going to be right here. So this is where the magic will happen, where we're going to have a line split. But we got to figure out exactly where the y-intercept is located. And the y-intercept is always denoted whenever x is 0. So when x equals 0, it's pretty straightforward. So that means that y will equal, well, it looks like since nothing can be divided by 0, the whole equation completely goes off. So there is no y-intercept. Cannot divide by 0. Doesn't make any sense. So there is no y-intercept, and so we can just pinpoint this bad boy over here, and it will just go in its normal fashion between the curves, as we already know. And the whole equation that we know, let me just put this right here, 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 and here. So we have -infinity to -3, all the way up in unison with -3 to positive infinity for our domain. Let me just make this and put it back over here. Clean this up a little bit more. There we go. Nope, there we go. Infinity to positive infinity, and the ranges, the same case, -infinity to -3. Unison with -3 to positive infinity. All right, and so let's move over to our next. Let's focus on our next function, square root functions. And now we're going to go over the square root functions and literally square root functions as well. So really what we are focusing on between them is that they both have a similar structure in nature. It's just the differences is that literally square root functions, there's going to be some type of constant that transforms our given slope and our x-coordinate as well inside of the square root, as indicated in the second part of our images that we have. So we notice in particular, depending on the nature of how our square root is already set up, from the basis of just square root of x, when we start at 0, it goes all the way out in the positive direction, indicating that our domain is going to start with 0, goes all the way out to infinity, and then also does the same thing for the range, starts at 0, and goes all the way up to infinity as well in the positive direction. Now, if we were to have a case where we are subtracting x from 4, technically what would happen is that there's going to be 4 over here on the x-axis and 0 as well. It's going to go all the way out to negative infinity as we are subtracting, since we have a negative, negative over here. And then we're also going to have 0 as well, given the fact of our y range starting over here, and we have our literally square root function starting between y, and then we have x over here. Hence we already see the following. Just zoom out so you can get a better understanding. And now let's head over to our first practice problem. Now to go over our first practice problem, we are denoted with the function of f of x is equal to the square root of x plus 2. So in order for us to be able to figure out exactly how this entire graph will actually be laid out, what we can do to be able to set it up is that the series of steps we need, and have to first figure out exactly one, where the starting point is going to be. since we are dealing with a square root function, square roots have starting points. Then we would have to determine the domain and range for such. And so we're able to figure out such. If we were to set first our starting point to be 0, so we would have, I'm just going to focus at the first step over here and just zoom out. There we go. So for first step over here, what I'm going to be doing is I'm going to set y is going to be equal to 0, which we just plug in for f of x, so it's 0 is equal to the square root of x. It's 2. We square both sides. We get 0 is equal to x plus 2. We just subtract 2. We subtract 2. And so it's equal to negative 2. And when y is 0, so it's y. So we have negative 2 and 0. This is our starting point to begin with. So let's draw the graph. And since we are dealing with a positive direction as well, this is how the graph is going to be determined. So we would do 1, 2, starting point, 1, 2. And since we're dealing with square roots, typically it will just be 1, 2, 3, 4, 1, 2. That's just the nature of how the graph is actually going to be going. So it's going to go up every single square point that we have, but it's going to be having a unique starting point. So we have 1 and 1, and then we have 2. 2. It's going to keep going, just in this part. So we can therefore say that our domain is going to be negative 2 all the way to positive infinity, and then our range is going to be 0 all the way to positive infinity as such. Let's just zoom out. And then finally, let's go work on our second practice problem. Feel free to take a screenshot of this part too. And so let's go over our second practice problem. So in our second practice problem, we're given the function square root of 3 minus x. And so when we have done so, what we need to do first is find our starting point. Then find our y-intercept and figure out the domain and range. When we've done the following, let's just start things off. So for us to be able to configure our starting point, for any square root function that we have, we're just going to have y is going to be 0 at one point, and that means we just got to configure what x is. So let's just get this thing started at 1. So we'll have 0 is equal to the square root of 3 minus x. So then we square, and it looks like, oh wait, 0 is equal to 3 minus x. It's 3 minus 3, and it looks like x is going to be 3. The reason being is because when we move this 3 over, in fact, just to make things clearer for everyone, it's negative 3 equals x. We can just shift this around, then divide by negative 1. Nothing changes. And then we just have x is equal to 3. So that's our starting point. Then we have to figure out the y-intercept. And it's super, super, super easy. All our y-intercept is when x is 0. And it looks like it's just the square root of 3. That's pretty much it. That is our y-intercept. That's when we plug in 0 to here, we just have the square root of 3. And then we have to figure out our domain and range. So that's the easiest part. Let's just go all the way down. Let me just build this out for you guys and gals. All right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 5. 1, 2, 3, 4, 5. All right. So when x is 0, here, looks like, yeah, right here. That is where our y-intercept is. And since we know where our starting point is, it's going to be here. So that means we're going to move this thing over here. It's going to keep going all the way out. As such, and our domain is going to be, and the reason why it's actually going out that way, aside from our y-intercept, is because we have negative x this way. That is really just the main reason why. Then we have x being equal to 3. So from our domain, it is going to be 3 all the way to negative infinity. And our range is going to be 0 all the way to negative infinity. For we know that the domain is x, and just y. Just close on. And feel free to take a screenshot of this, and let's head over to the vertical line test. Hey everyone, thank you again for taking time to watch this video. If you found this video helpful, be sure and feel free to please like and subscribe, smash the like button, and ring the bell for any notifications as well. And if you have any other questions, by all means, feel free to put it in the comment section as well. And as always, take care. Cheers. Bye-bye.